Hi folks, this is Stephen Tyler, and this is the second half of section 7.2-3, Rules for Means and Variances. Okay, let's pick up where we left off on section F, some more rules right here. And then you had these guys, so these were our variance rules, you guys. So when you're adding variances together, you add their variances together, okay? When you subtract the variances, it's also adding their variances together, and it's because you're squaring them, so that makes that positive every time, okay? And then we had if they have a correlation. I want to go in a little more in detail on this. Then you got to include your correlation. Now your correlation is when they're dependent on each other. Okay, if they're independent, then we don't have this worry about this correlation part right here. So and we'll talk about dependence and stuff in just a little bit. And same for this one right here. If you're subtracting them, then we're going to subtract off minus 2 times the correlation times the standard deviation of x times the standard deviation of y. Okay, your standard deviations of x's and y's are just the square roots of your variances of your x's and y's. Okay. All right. So the correlation is always between -1 and 1. It measures the direction and strength of the two variables. Okay, and the correlation between two independent variables is 0. So if they're independent, we don't have a correlation, you guys. So this, we don't have to worry about it. We just use these guys right up here. So up here is when they're independent, and this stuff is when they're dependent. So I don't know if you have that written in there, so go ahead and write those in your notes. All right, let's do a few examples here. Here's section G, winning the lottery. Okay, so this is example 711 on pages 421 and 22. Okay, and we're doing that tri-state. The payoff X of $1 tickets in the tri-state pick 3 game is $500, and the probability of winning is 1/1000th and 0 for the rest of the time. So here's the combined calculation of the means and the variances, okay? All right, so 1x is you win $0 or you win $500, okay? And the probabilities of winning $0 is 0.999, and the probability of winning 500 is 1/1000th, okay? And then so when you multiply these, when I do this number times this number, I get 0, and 500 times 0.001, I get 0.5 right there. So the mean of these two x's is the addition of these. So we just add these two together, and that's the mean of x. And then over here, to calculate the variance, you guys, we got to do each number minus the mean squared times the probability. Okay, that gets me that over there. Then this number minus the mean squared times its probability, and it gets me that over there. And then we add those together, and this is my variance right there. Okay, and so then the standard deviation, gang, is the square root of that right there. So the square root of that is $15.80. And it says it's usual for games to have a chance to have a large standard deviation like this because large variability makes gambling exciting. If you buy a pick 3 ticket, your winning W's are x minus 1 because the dollar you paid for the ticket must be subtracted from the payoff. By the rules for the means, the mean amount that you win is the mean of your win. That's what this says, mu of W. The mean of my win is my mu of x minus 1. Okay, so remember my mu of x is right here, the 0.5. 0.5 minus 1 is you're on the law of large numbers. You lose 50 cents every time you play that game. Okay, but the large standard deviation makes it exciting and it makes you guys want to play more. All right, so that is you lose an average of 50 cents on a ticket. The rules for variance remind us that variance and standard deviation of the winning W equals x minus 1 are the same as those as x. Subtracting a fixed number changes the mean, but it doesn't change the variance. Okay, your variance stays the same when you add or subtract. Only your means add or subtract 1. Okay, so suppose now that you buy a dollar ticket on each of 2 different days. The payoff x and y for the 2 different days on the 2 tickets are independent because separate drawings are held each day. So your total payoff is just x plus y, and that would be have your mean, x plus y. So your mean of your x is going to be the 50 cents for one day, the 50 cents for the other day, which is a dollar total. All right, so because x and y are independent, the variances of x's and y's are just the sum of the variances squared from that formula that we just did. It doesn't have the correlation because they're independent of each other. Okay, so the variances that we just calculated was $249.75 and plus $249.75, and you get almost $500. So the standard deviation of that would be the square root of that, which is 22.3. Okay, now notice this, you guys. This is not the same as the sum of the individual standard deviations. Remember, each individual standard deviation is 1580 and 1580, which is 3160. So variances of independent variables add, and standard deviations don't. Okay. All right. So if you buy a ticket every day, 365 tickets a year, your mean payoff is the sum of the 365 days. So that means you get 50 cents each day, or $182.50. But don't forget, you paid $365 to pay. So the Tri-State, on the law of large numbers, they collect from everybody $182.50 if they play every day. Okay. All right. So here's the old SAT score. So SAT math scores would be X. So the mean of X is 650, and the standard deviation is 90. The verbal scores, they're going to call it Y, and the mean of Y is 590, and the standard deviation of Y is 100. Total overall mean, and this is going to be the rest in 712 on page 422 and 23. So what are the mean and standard deviations of the total scores, okay, among the X plus Y students applying? So you just add your averages, you guys. So you add those together and you get 1250. Okay, that's easy enough to understand. Okay, so the variance and standard deviation of the total cannot be computed from the information given, and this is why. SAT verbal and math scores are not independent of each other, because students who score high on one exam tend to score high on another. I know there's exceptions. Some of you guys are good at math and not good at English, and vice versa. But in general, you guys, if a person who's good at math, they tend to be better at English as well. Therefore, Rule 2 doesn't apply, and we need to know what the correlation is to even apply Rule 3, you guys, and they didn't give that to us. So let's go ahead and give that here. Here it is right here. So suppose that their correlation is 0.7, okay, and they're independent of each other. They're dependent of each other. So if this is true, then we can go ahead and use this formula right here, okay? And so our standard deviation, we square those. That'll give us our variances, you guys. So the variances, the standard deviation squared, is plugging them in. All I'm doing is using that formula right up above. There's the 2, there's the correlation, there's the standard deviation of X, the standard deviation of Y, and we get 30,700. So the variance of the sums, X plus Y, is greater than the sum of the variances, because the positive correlation between the SAT math scores and verbal scores. Okay, or that, in other words, the X and Y tend to move up together and down together, which increases the variability of their sum. And we find the standard deviation from their variances. You just square root that, so it's 175. So, okay, so when they ask you to do that, you just plug them in into your formulas there. So investing in stocks and T-bills, example 713 on page 423. Zadie has invested 20% of her funds in treasury bills and 80% in the index fund, and it represents all U.S. Common stocks. If X is the annual returns on T-bills and Y is the annual returns on stocks, her portfolio return rate is this, 20% of X and 80% of Y. That's easy enough. Okay, so the returns X and Y are the same variables because are random variables, because they vary from year to year. Based on annual returns between 1950 and 2000, they have found that the mean of the X's was 5.2% and the standard deviation 2.9, and the mean of the Y's is 13.3% with the standard deviation of 17, and the correlation between them was negative 0.1. All right, so let's do some calculating here. So stocks had higher returns than T-bills on average, but the standard deviation shows that the return on stocks varied much more from year to year. Which means it's more risky, you guys. So, I mean, you're thinking, gosh, if you make more money on stocks, why don't you put all your money in that? Well, it's more risky, and a lot of people did back in, 2007, and they lost a lot of money. Okay, so because they were riskier. So for the return rate on Zadie's portfolio of 20% and 80%, there's a return rate right there. And then so the average of a return rate is just going to be 0.2, because it's 20%, times the average of the X's, which was given, and 0.8 times the average of the Y's, which was given. So we're going to plug those in. So when you get that, you add them all up. So her average return rate is 11.68%. Okay, easy enough. To find the variance in portfolio returns, we're going to combine rules 1 and 3. Okay, there's the formula that I showed you a couple slides ago. Okay, so we're going to use that. And when we plug it in, remember the 0.2. Here we got that from this formula. I think I put it right there. Yeah. So when you're multiplying stuff, it comes out here and becomes squared with that right there. It's just a formula. So that 0.2 came out and became squared, and that 0.8 came out and became squared because of the formula right there. And then just plugging in all the numbers right there. Okay. And when you plug those in, don't forget they gave us this information over here, so those got plugged in for the variances there and the variances there. Okay, so everything got plugged in, and we're going to find that the variance on the return, on her returns, is $183 and about 72 cents. Okay, and her standard deviation is about 13.55%. Okay. All right, and then we're going to do a round of golf, sample 714 on page 424. Tom and George are playing in the club's tournament, and their scores vary as they play the course repeatedly. Tom's score X has the normal distribution of 110 with standard deviation of 10, and George's score varies round and round with this normal distribution, 108 standard deviation. Okay. So if they play independently, what's the probability that Tom's score will be lower than George's score and thus do better in the tournament? Sorry. So we're looking for the difference between their scores, okay? Because Tom has the higher score. So the x minus y would be the difference between those two guys. So 110 minus 100 is 10. So that would be the difference between their scores on average, you guys. That's the average difference. And then the variance, you guys, is just plugging them in because they're independent of each other, you guys. So we don't need the correlation on this. So square them and you get 164. And because 100 square root of that is 12.8, then the difference of their scores are going to have a normal distribution of 10 with the standard deviation of 12.8. Okay, I'll show you this figure in a few slides later, you guys. Okay, so let's go ahead and crank this out, you guys. We want to know what's the probability that Tom's going to be less than George. Okay, remember George was y and Tom was x. Okay, if I subtracted this inequality, subtracted y from both sides, look what happens. I get x minus y is less than 0, so that's the same thing right there, you guys. All right, and then we want to know, since their difference is 10, what's the probability that when I take off 10, because their difference is 10, so this is going to be my z-score right here because their difference is 10. We want to know when is it going to be lower than 10. Okay, because Tom is always higher. We want to know when's Tom's going to be lower than 10, so we took off 10 on both sides. Okay, when I crank this out in the calculator right there, I get negative 0.78. This is my z-score. So when I look up negative 0.78, I get about 0.2177, which means almost 22% of the time Tom's score is going to be lower than George's.